Talking about question 3 on homework 3. And so the first part of the question asks us why we have to discuss two different circuits when discussing noise margins. And that's because the two margins are defined, their two extremas for each margin are defined by output signals from the first circuit as well as input signals that are interpreted by the second circuit. So we'll describe that in a little more detail through this example. So the first values that we have to find are the absolute minimum and absolute maximum output voltages from the first circuit. And so what we can do is look at this voltage transfer curve. And since both circuits are the same, they're cascaded inverters, we can use this transfer curve to describe the behavior of both circuits. So for circuit 1, the absolute maximum output voltage is defined as 6 volts, as we can see from the y-axis here. We'll be looking at the y-axis to describe the outputs of the first circuit. We can also find the absolute minimum output voltage from the first circuit as half a volt, as indicated by the y-axis here. So now we have the two maximum and minimum values that the first circuit can output to the second circuit. The next thing we have to do is discuss how the second circuit interprets input voltages. And we do that using two lines of slope -1, and we determine where on this voltage transfer curve are the 2 points which have slope -1. So we'll approximate that here with these lines. Let's say one of them's about there, and the other one's about there. That looks good enough. These are rough approximations, but they illustrate a point. So we'll define this first value here. And remember, we're looking at inputs to the second circuit. So let's look at the x-axis. This corresponds to lower input voltages to the second circuit. And so we're going to define this as VIL, input low. And this is the maximum voltage that the first circuit can send to the second circuit that the second circuit interprets as a logic 0, or as a low voltage. And judging by here, this is 2.25 volts. It's a little bit to the right, so we're just going to say 2.26 volts as an approximation. And similarly, we are talking about inputs to the second circuit, so we have to look at the x-axis. Here is 3 volts. Well, maybe let me first define this point. This point describes the minimum output voltage that the first circuit can send to the second circuit that the second circuit interprets as a logic 1, or high voltage. So we can define that as VIH. And this is 3 volts, this is 3.25 volts, so let's approximate that as 3.13 volts. So we now kind of have 2 points for each margin that define the lowest logic 1 and highest logic 1 that the second circuit can receive, and sort of the lowest logic 0 and the highest logic 0 that the second circuit can receive. So let's go ahead and define our noise margins now. So our high noise margin will be determined by the maximum output from the first circuit to the second circuit, as well as the minimum voltage that the second circuit interprets as a logic 1. So here that's 6 volts, and that's 3.13 volts. So let's take out the calculator. That's 2.87 volts. And that describes the range of voltages that or the amount of noise that can exist on a high output from the first circuit to the second circuit that the second circuit will accurately be able to understand or interpret. Next, we're going to do the highest low voltage that the first circuit can send to the second circuit that will be interpreted as a logic 0, as well as the lowest output voltage that the first circuit can send to the second circuit. So the highest low voltage we can say is VIL, and obviously the lowest voltage that it can output is VOL. So when we take the difference of these, we get 1.76 volts, and this defines the range of voltages, the range of low voltages that the second circuit can interpret correctly. And it defines also how much noise the output signal from the first circuit to the second circuit can handle. The last part, part C of the question, asks us to determine Vm, which is called the switching voltage, and it's defined by the point on the voltage transfer curve where Vin equals Vout. And so we can use a line of slope 1 to describe that equation, Vin equals Vout. and we can see where on the voltage transfer curve this point lies. And it looks like it's about here. So let's go ahead and define VM. Again, it's relative to the, well, it doesn't really matter which axis you use, I guess, but it's a little bit below 2.75 volts. Let's just call it 2.7 volts, just to make it a little bit easier. And this is called the switching voltage, the threshold voltage. It's halfway between sort of the maximum logic 1 and the minimum logic 0 voltages. And so we can kind of describe that as where the input to the second circuit switches from a high to a low, or a low to a high. So that should cover question 3. Thank you very much.